So we start with our first session, and yeah, our first speaker just arrived on time. And so I will introduce Professor Haddadin. He is the head of and director of MIRMI at TUM and holds the chair of Robotics and System Intelligence. And he will speak about AI-based knowledge discovery, the quest for science automation. So I'd like to greet Professor Haddadin, and please come on the stage.
WLAN?
WLAN sollte hier sein.
Ist das welches? North?
Das Pacifico, ja, genau. Also ein von beiden.
Okay, great. Konnte nicht eingestellt.
Okay,
gut. Still fighting with wireless. This seems a bit better. Okay, great. Dennis, thanks so much for the intro. And as said, just on time. So, first of all, let me thank the speakers, the organizers for putting together such a workshop. I think that was really a fantastic idea, and that's something I'm happy to support. And I think it's a very important topic, which we have been working in the secret for many years now, and we try to kind of now surface a little bit with all our works over the last maybe year or 1.5. Still the early stuff. But I think it's really important to think also in terms of, how can we as a society, as a scientific community contribute to this big quest of AI for knowledge discovery. And in particular, if you think about robotics, what can we do? We can do the act, right? We can do the heavy lifting. And the quest for science automation is kind of deeply rooted in this idea of, Greek ancient thinking, whether it was like that or not, but I always like to think of us ideally being aligned with Raphael's famous picture of the ancient Greek philosophers and scientists, in the sense of thinking more than acting and running around. And in particular, I mean, I'm now trying to take also the stance, in particular of students in the natural sciences, experimental natural sciences. So that seems to be more their life, right? So it's really. I always loved PhD comics as a PhD student, so I always felt very kind of affiliated to this particular picture because I was also in the lab all the time. We didn't have Windows, by the way, at DLR back then. So I think it's really important to think not only in terms of robotics for society alone being applications, but also for the greater good of science, I think. And we have a lot to offer. We don't think so much as roboticists as being tools to others. We actually think in terms of, building machines that do certain interesting behaviors, instead of also more and more thinking about robots being assistants and accelerators of scientific discovery, of scientific work. And in particular also freeing, we always talk a lot about the 3Ds in robotics, dull, dangerous, and dirty, but we don't talk about so much about, how to support the scientists in the lab environments to actually get the job done. I always love this idea of a lab Jarvis. So the idea, I'm not sure who's familiar with Jarvis, that's the famous super robot, super AI that helps Tony Stark to not only design his exosuit, but in particular even do scientific discovery, so finding new elements and becoming a sentient being by itself, but in particular also, I think at some point even help solving time travel, which I think sounds like a great idea. So the question is a bit, how can we really do that? And there has been over the last years a lot of kind of work in AI-based knowledge discovery, especially in chemistry and biology, so natural sciences. So how can we kind of use state-of-the-art machine learning algorithms to, better either do certain experiments, assist scientific discovery. I think all of you have heard also about the most recent publication from Google DeepMind with AlphaFold 3. So I think it's quite amazing. Also, we're working together with Helmholtz here on several things, which is kind of the National Health Center. And they built, for example, what we call an integrated cell atlas, being part of an international initiative there. So I think it's very clear that AI is becoming more and more important. I mean, we use the word discovery a lot. I'm not so sure whether everything of it is discovery per se, but it's exploration of a high-dimensional space that we are very bad in as humans to actually explore and get that done. So I think this is really a very, very important work for, I mean, very early on in the scientific discovery, which I think accelerates, I mean, orders of magnitude over the value chain until things reach products, of course. I think what is, however, also at the same time important is that it's not only about the, you know, the data analytics, the let's say machine learning on well-curated data, which, you know, you, or maybe not so much our community, but the community of natural sciences has to generate. And generations of PhD students, junior postdocs are creating lots and lots of data, and it seems that their work is really, you know, a lot of lab work before the scientific discovery really comes. And in this kind of problem space, I think it's very clear that science automation would be super important to tackle. I mean, we all know that in chemical industry or in drug, let's say, production of, I don't know, all kinds of products, large-scale automation is already there, so lab automation exists, there's nothing new. But the big question is, can we actually automate the scientific process, which is kind of related to this idea of you know, product lot size 1 in factories, and Birgit is also with us today, so we have been talking a lot about these concepts over the last years. How can we really automate processes that have to be automated exactly once, and not in the typical cycles of you know, months and years typically to create such an experiment. And I also like the idea of, you know, Hiroki Kitano was I think he's CTO at Sony in the science labs. So he kind of pushed out, this was actually my last travel before the pandemics to Shenzhen. Back then there was a nature conference on launching nature machine intelligence. And he kind of explained this idea of the Noble Turing Challenge, which kind of, you know, resonates well with us as a community, because the idea was, can we create an engine for scientific discovery, which I think feels really something that could be doable. Obviously super ambitious, but still, I think the thought experiment is really good to do. And I think we all remember this paper in Nature in 2020. It was called The Robot Chemist. I mean, in the end, the robot was basically kind of supporting the lab work coming from A to B. So many roboticists told me, why is this a robot? That's not a robot. No, you got to think of it that way. How does a robot support the discovery? That's the question, right? So it's really important to see how our technology becomes a tool. And I think being a tool is the meaning of being useful. And that's something I believe we should be thinking a lot about. So we have seen lots of works, very highly published and cited. I think it's really interesting. Already 2009, there was this, I'm not sure you were aware of this, but I thought this was a very interesting paper, the automation of science, kind of forethinking how we could really work on such things. Most of the work, however, is if you go to robotics in the scientific space, it's mostly screening, so that you try to, you know, do high batch works. Also, if you go nowadays to big biotech companies, maybe 10 years ago, they were very little, I think, automated in the, you know, in the discovery or in the functional spaces. If you nowadays go to big companies like Roche or others, they basically become data engine providers, because they kind of automate and digitize the entire processes, basically preparing to what we would then call the automation part of it. Okay, so what do we actually want to do? I mean, the natural science discoveries requires basically 3 things, right? So the curiosity-driven thirst for knowledge, you could say. So we want to ask fundamental questions. Then we spend typically years, actually years, sometimes decades, to do the right experimental design, and then actually come into the knowledge discovery process, right? So I think what is, however, very clear is that there's huge challenges. So the 3 steps I just showed you are the lifetime of a PhD, or lifetimes of many PhDs, if you think as a professor, so you think in decades typically. And if you look at the costs and the challenges that are there, it's very clear when you talk to natural scientists. And not only to let's say, laboratory work, but also if you go to the big accelerators like CERN or DESY in Germany, probably the SLAC, they're going to tell you the same, that they really have promise in automating experiments and doing it in a highly efficient way. So I think this kind of is an important aspect in various dimensions, but I think there's like 4 important aspects. I mean, the experimental costs and efficiency. So it's a lot of work. Reproducibility is an issue. How can you make use of, this workflows that are developed in the world, and how can you really, I think, roll them out? The effectivity of researchers. I mean, how much of your time do you spend? It reminds me a bit of deep learning, to be honest. So how much of your time do you do in the scientific work, and how much do you do in, let's say, crafting and trying out and experimenting to finally find something that really produces the right data that you want to do your research about? And then there's the reproducibility aspect. It's even talked about the reproducibility crisis, because complex experiments require complex standardizations of how to acquire the data, how to process it, and in particular also how to interpret the data. And then obviously there's also lots of questions about safety, health. I mean, whoever has developed biolaboratories who have been trying that for quite some time now, took forever, takes forever. It seems to be really quite an effort until you finally end up where you want to be, and the processes themselves are kind of a big damper in the knowledge discovery process itself. Okay, so we need to develop intelligent lab environments. I think that bridge between AI and robotics, meaning physical assistant, obviously enhanced and accelerated by the right algorithms, but in particular physical assistance is something that we want to put our focus on. Why am I saying that? If you look at this, conventional experimental knowledge discovery cycle, which is very slow, as we all know. So you've got these experimentations, right? So that's kind of a very big process. You try to generate the samples. I mean, if you think about AlphaFold, many people basically were data engines, data crawlers, right? Many PhDs are essentially, their whole purpose is to create a data point in an AI engine. That's kind of who you are. So I think that kind of is how we should look at it, because then we also understand that everything in the cycle is basically state measurement, right? Then comes the single level or single cell, for example, qualitative outcome. We screen, we generate the data, then we do the learning and planning, and then hopefully generate a good next recipe, right? That's kind of typically how it's being done on a very abstract level, of course. I think we do the same essentially in algorithmic developments, but I think it's interesting to see where the resources really go here. So it's in the experimentation development. State measurement is still ancient, I think. It's kind of interesting if you look at it. So the devices are very, very, manually designed. And the next thing that has been happening was through AI acceleration, trying to kind of, assist the state measurement and assist the learning and planning. So this has been many of the papers I showed you. But this is still not the, high acceleration. Why? Because all the work has been done already, right? So all the manual work is actually in the first part, where millions of researchers are, using their body to create data, right? That's kind of who they in the end are. So we need to really work on automating the experimentation capabilities drastically. So that's kind of what we want to do in our lab. I mean, as probably many of you know, we have been pioneering many of the robots that people are using nowadays in the world. Also the robot chemist, so that was the KUKA lightweight robot. I was myself one of the developers of it, not at KUKA, but at the time at DLR, so when we were developing the basic science behind it. So it was great to see that a system that you developed, that was originally developed for space applications, a space robot, that became a commercial product in industry, and then at some point, 20 years later, voila, it became a tool to accelerate science, right? And nowadays, people are using these technologies to do that on an everyday basis, which I think is really a fantastic thing for us as a community. It is not as rewarding as doing 1 year of research, 2 years of research, going to ICRA. People are amazed by it. It's a bit longer term plan, I guess, but I think as a community we should be doing that. Okay, so let's come to some very early results. I just wanted to share that with you. Still not on the large scale, but I think it's interesting to see what we have been doing. So Dennis has really been amazing in pulling together this intelligent lab assistant. So we are developing all kinds of skills that we want to kind of deploy in the laboratory environment and make them basically simple assistants that do all kinds of general purpose skills, from storing, opening, closing, all the things that in robotics we think are solved, but they are not available, they are not accessible to the laboratory environment. So we really try to build a system that is also fully digitized, a full digital twin running on parallel, So this is obviously huge heavy lifting to develop such a system, and the reward is in the end if you have it, right? So really if you can put it into use. So it's not on the way so much. So it takes quite some time. So Dennis has been working with his students and other students of mine really on kind of, developing various tools, automating the hell out of everything. It's really a lot of work until you come and even automate centrifuges and scales and so on. So still in process, but we're getting there, I think. It's kind of very interesting how far this takes us. So I will just do this very quickly. I'm sure Dennis is going to talk about many of these things as well. So I'll just give you a little bit of glimpse. There's already some papers right now out. Some of them are still in preparation, but I think we wanted to share it here. So, I mean, especially safety, I talked about that. So we want to use these robots really to do also the heavy lifting in the safety space, or to also run experiments that potentially are hazardous, so that you don't have to go through the processes, always for the human workers, or for the lab technicians and lab assistants. So ideally, we want to even be able to operate these systems from home, right? So you basically start your experiment, everything runs then in the lab, and you come back and hopefully have the experiment. One thing that I was a bit naive about that, but then the biophysicist told me, okay, that's the actual grand challenge in lab automation, is the individual pipetting and making it extremely accurate. And I always say Dennis was pipetting the hell out of every robot. So he's now pipetting at levels that are beyond what any human can do. So higher accuracy, better quality. And this has been really a challenge, because so far the lab automation in pipetting is mostly high throughput screening, and the accuracies and the volumes that you can really do accurately are not even close to where you need them in the discovery processes. So why did we do that? Because of a process I'm going to talk about in a second. So after I'll just very quickly try to sketch kind of the big picture of what we do. So basically what we want to develop is a self-evolving learning experiment. So as I said, lab Jarvis. So let's say that you want to build this AI system with a digital twin that is connected here. Then obviously the idea is that it has the ability to learn, can change its end effectors, new skills, be trained. So for the ones who saw my plenary, I was talking a lot about creating skills on the fly, zero-shot learning. So the work that we have been doing in fundamental robot learning and robot skills is now kind of being directly translated. So if this wouldn't have taken place, then I think this would be a quest that could not be successful. So I think really that there's a very clear direct translation. We call this use-driven basic research, right? So it's not the classical basic research, application research, but this is really something in basic science directly translating into another field. And in the end, what you want to basically have is this experimental execution. Okay, that sounds like I'm running out of time, but I'm almost done, Dennis, don't worry. I'm not exaggerating here. So I think what is really important here is now that these kind of experiments, the execution, the evolution of the experiment is kind of where we want to run, but in both ends. So in the execution evolution, but also in the synthetic direction. So we also want to be able to synthesize new materials, for example. I'll give you an example in a second. And then obviously you have this, two processes: the system identification of what kind of mechanisms we want to develop, natural systems that are supposed to be identified. So system identification is obviously something that can live a lot or live on these things. And then I have this, the synthesis question at hand. And what do I mean by synthesis? That's something we're doing together with Hendrik Dietz, who's a very, very renowned biophysicist for DNA origami. And his big question is basically, how can I synthesize DNA origami molecules? At the moment, he's on a functional level, but the big question is, can this scale up to more complex systems? And one thing that he was proposing as well during the pandemics, I think everybody tried to relate the research to the coronavirus. He was kind of talking about trapping viruses in these systems, which I think was a very compelling story. But he's kind of thinking of much broader applications on these systems. Okay, so how can we now help there? So our idea is to upgrade and really optimize nanobots on morphological and various dimensional parameters. And for this, we are building this, synthesis pipeline. So this is now a discovery loop in the sense of new materials. So we basically have the toolbox of robotic nanobots that the recipes are quite well known. There was lots of Nature and Science papers on that. And then we basically try to sample the space, improve the quality, use, for example, the idea of how, let's say, for example, in a cancer cell, can we actually, deploy these systems, then do the microscopy on it automatically. We actually use super resolution microscopy at the moment in the lab to automate, then do classification, on the cellular level, then do the learning loop and feed that back. So that's kind of what we're working on at the moment. I think we're pretty close to closing the loop for the first time, if I'm not mistaken. All right, and with this, I think that's also the team that is working on that. That's actually the guys who are involved, and as you can see, Dennis is always at the center, and then we have also Henning and Moritz, who are more working on the knowledge discovery, and then on the microscopy, so autonomous microscopy is the big topic of Henning, and then also Andrea is pulling everything together as the lab manager. So these four are kind of trying to create this knowledge creation engine. All right, so that was actually what I wanted to talk about. I hope it was kind of interesting to see how classical roboticists who actually do basic science in robotics are now trying to help the natural sciences to accelerate. So I hope that in 50 years they will say, boy, these guys really made our lives easier. Thank you very much.
We're gonna switch now to our spotlight poster session. So we encourage all poster presenters please to line up and come on the stage each by each, and I will put up the presentation for them.